other vehicles on the road. So is there any chance of, suppose if the speeds are mismatched, is there any chance of accident happen, it means any collide with that vehicle or not? Okay. And how to identify means a traffic pole, right? And how to identify the traffic timer also. Traffic timer, and whether the timer is which color, red color, green color, or yellow color, right? And if the red color, what is the timer value and how much time it has to wait, right? So these things, as human, what we'll do, these things should be done by the autonomous vehicle also. And any obstacles like any animals present on the road, or any animal is moving towards the vehicle or towards the lane or towards the road, right? Is there any chance of accident, whether that animal or human or some other obstacle is moving towards or moving outside, away from the vehicle? Like that we need to identify, and if that situations are there, so we need, it has to take, we have to give that as input to the autonomous vehicle so that it will take the necessary actions. So here, these are the frameworks we developed. First and foremost, for any vehicle, as a driver, as when we are driving, we need to go on a single, on a lane, right? There will be multiple lanes. If you see in roads, there will be multiple lanes, right? So on which lane we have to go, right? So first we need to identify the lane. Then the next work was traffic pole detection and the counter, traffic pole detection and the counter, the timer detection, right? How much time it has to wait, or if that is a green light, so what may be the means, how many seconds there is a still there is a chance to go, right? Like that, we will do this. The third one is vehicle to animal accident detection. Is there any chance of that whatever we discussed, any animal is there on the road, means that particular lane, or it is approaching towards the road, or it is going outside the road? Okay, animal or whatever it may be, but we did with the animal. Then vehicular accident detection. Is there any, suppose what I said, suppose the same lane some other vehicle is going on, other vehicles are going on, right? So if we need to identify, right, what is the speed of the vehicle before to us, and what is our speed. If we increase our speed, then is there any chance of collide, right? And one more thing here we'll address is, suppose if there is a, let us an accident happened on the road on that particular lane, right? So how to identify, right? So we have to slow down. This vehicle has to slow down if some accident happened there, right? Generally accident means, there may be collide with some other object or some other vehicle, right? So if its speed, their speed, suppose if we identified that vehicle or object, and if its speed is zero, means they are not moving at all, means we can assume there is a accident. But if they are slowly moving or they are moving, then we can say that there is a, they are on the road, they are moving, right? No accident. And the last one will address is the potholes the road. This work we did very, means it is still we need to do a lot of things in pothole, but these four, all these works are published already, right? The first one is lane detection. So steps for detect here, these are the few steps. You can see first we need to the cam whichever there on the vehicle will capture the road, right? Capture the road, this front side of that vehicle, right? So this is that. Now second step is pre-processing. The second step is pre-processing. Pre-processing means So whatever the image captured using the camera, maybe means low quality, or generally the quality of the image captured will depends on the camera resolution and the weather conditions, the current weather conditions, right? If that is rainy, means we can have low quality image, or that is dark, means in night mode, generally we will not have that much clarity, means good image, right? So anyway, in any image processing problem, the first step means after capturing the image, we need to pre-process it. Means pre-process means we need to reduce the noise in that image. We need to reduce the noise in that image. And also increase the contrast. Increase the contrast means image enhancement, we can call it as increase the contrast of the means making more means apparent, means we need to use some filters to reduce the noise content in the image, and we can use some mechanisms like image enhancement, like mechanisms like histogram equalization, or some other methods to increase the quality of the image. So that we'll do in pre-processing. Okay. The third step is so here after capturing the image, our ultimate goal is to identify the lanes, right? Identify the lanes. You can see here the lanes are in white color. Okay, the lanes are in white color, and the road is in some, this is the blacktop, right? Blacktop roads, right? So they are in so means they are compared to this lane color, right? They are darker colors, right? So how to segregate, or how to detect, means how to only means identify the lanes is can use some here edge detection algorithms. Edge detection algorithms. So the famous edge detection algorithm is Canny. Canny edge detection algorithm. Uh, okay, so what it will do, actually the Canny edge detector algorithm will identify the sharp intensity changes, sharp intensity changes, and they will be they will be means they are identified as the edges, or they are identified as the some borders of that particular colors. Suppose if you can see the above the top of the image is a sky, right? This is all sky. This is all sky, and after that there is a greener area, right? If you come down, there is a greener area. So the sky is in of color, so the sky is in color blue, and suddenly there is a color change, right? The color from blue to green, suddenly there is a change of the color from just see here, this one. So the candy edge detector will identify these sudden changes. Suppose now after this greenery, again there is a black top. Then some cars are there. Then there is a white. See, there is a white color, right? Again black top. Then again some white color, right? Again this black top, right? Again there is a white. and here suddenly some gray color came here, right? Again there is a color change. Again there is a color change. Any questions? Any questions?
No, sir.
Somebody, okay. My voice is clearly audible, or any disturbance is there, sir?
It is clear, sir.
Okay, fine. So, to identify these sharp intensity changes, so actually they are called the we can call them as some edges, or okay. So, to identify those sharp edges, okay, we'll use this canny edge detector algorithm. This is the oldest and efficient edge detection algorithm in image processing. Oldest and efficient, okay. Nowadays means this is the one which most of the research people will use. Okay, directly it will be available in Python as well as in MATLAB. Also, this canny edge detection function will be available to you. Now, the output of the output of this canny detection algorithm you can observe here means these sharp edges, the white colored, these are all sharp edges. See here, these are all sharp edges. Okay, these are all sharp edges. You can see here from the image, input image to the image C. Okay, so these are the identified edges. Now we need to remove the unwanted areas. So what is our goal here? We need to detect the lanes. So here the canny will detect all the edges in the image. But see here, all the edges means this variation from sky to this greenery, right? The sky to this greenery here, right? Sudden changes from this blue color to this green color. This will be identified. Likewise, this gray color means green to gray, and black top to. Okay, so our intention is to keep only these lanes, right? So we need to skip this unwanted portion. Now from this image we can easily observe the upper half of the image is simply that unwanted portion, right? It consists of the sky, some trees, and these things, but we are interested in the lane over the road. Generally this will be in the lower half of the image. So what we'll do here is we'll mask out the upper half of the image, since the lanes are present only in the lower half of the image. So what is masking? Generally, how we'll do the masking? So multiply that intensities, image intensities, with 0, nullifying the intensities. So how to nullify? Generally, we need to multiply with 0. So multiply with 0 is any value multiplied with 0 will get 0. So in image processing, the black color, the intensity of black color is 0. Intensity of black color is 0. So if we multiply anything by 0, we'll get black color, right? Suppose here this upper half, let's say this upper half is having some intensities, this upper half is having some intensities, right? This blue color. If we multiply these pixels, the pixels in this area with 0, what will happen? We'll ultimately get the upper half, the upper portion. This portion will becomes masked out, right? We removed the unwanted portion, right? This is the fourth step. Then in fifth step, we'll use some half transformation. These are okay. So in the previous figure, now you can see if we mask out the upper half of the image, right? So we have clearly the lanes we can see in white color, right? So this one and this one, right? Now this is this thing. Actually, this was in the previous with my pen I drawn that is not there in the image. Okay, so now using half transformation we will transform the pixel dots. So here actually the lane is represented with some connected means not connected dots, right? Connected pixels. So sorry, there are some pixels from here to here. Then there is no connectivity from up to this point, but we can have pixels in some form. See here in the third image C. Image C, you can see a portion of the pixels are actually not connected properly, right? They are not connected properly, the lane pixels, right? So half transform will use to transform the pixel dots observed as edges into understandable lines. Okay, the pixel dots observed over those edges means they are continuous, right? But there is small gaps will be there. So we'll use this half transformation method. So which sharpens the edges actually, which sharpens or which converts these unconnected dots into understandable lines. Okay, so then what we'll do, we will overlap means the now we have the understandable lines, right? Right, understandable lines. These will be overlapped into the original image. These will be the identified lanes, identified lines will be overlapped into the original image. Just see here, image F. Okay, so now you can see over the white these lanes. Now these red colored after transfer whatever the output that will be overlapped over that. Now then in the next step, we locate the most dominant line by taking the longest lines in the left and right slopes individually. See, actually our vehicle is here, right? Our vehicle is here. So using the slope, the longest line, because you can see some line from here to here, right? And in the right slope, we have a line like this, right? Now what these steps we will do, so by taking the most dominant line and in the left and right slopes of this vehicle, it will draw a straight. Using that slope, it will draw a straight line. So these are the identified lanes. Okay. Right. So at the end, we'll calculate the smoothing moving average on the identified locations of the lines to get the final markings. So this smoothing moving average will be used generally for time series data to identify whatever means the continuous values to predict the continuous values. So here also, while the vehicle is driving continuously, it has to fetch continuously it has to identify the lanes, right? So based on this moving average, automatically it will draw the it will find out that lines, that the lanes, and means that vehicle will be means proceeded in that way. So at the end, we have now the lines the vehicle has to go in that particular lane, right? The next framework, actually, whatever lane detection, this is purely based on image processing methods like canny edge detector and being simple histogram equalization for this one image enhancement and this masking, everything. These are simple image processing functions we used, the soft transformation and these things, smoothing, moving average, all these things are simple, means simple methods we use to identify the lanes. But from now onwards, for other support systems like traffic lights and traffic, that potholes and accident detection and animal detection, for all these we'll use a deep learning model. Okay, so now coming to the second support system, that is traffic light signal and counter detection. Okay, so this it consists of actually two phases. First we'll identify the traffic pole. Working properly. First we identify the traffic pole. Then second, we'll identify the timer. Okay. So this is the overall framework. See, this is the input image taken, and this will be given as an input to the some DL model. Here we are using mask Rcn model in this work. So the output of this mask Rcn is the cropped traffic pole. Cropped traffic pole. Okay. Then the traffic pole will be given as input to the other model, that is a RetinaNet model. So which will give us a detected timer. Okay. So anyway, we'll see one by one. So how these will work and how we'll get the traffic pole and this timer. So here for object detection, means the traffic pole detection, use this mask Rcn. Actually, we can also use simple object detection model mechanisms like YOLO also. You only lookup algorithm is an efficient, object detection model, but there is a specific purpose why we use this mask Rcn in our work instead of this YOLO. Actually, this YOLO will give us, simple the object class, the detected object class. Object class means whether that is a traffic light or not, whether that is a dog, whether that is a cat or a human. Okay, and it's what is that called, bounding box. The object class and it's a bounding box. Bounding box. Now, what is bounding box? This YOLO actually you can also observe in our mobiles. Suppose while taking some selfie or while you are taking a picture, a group photo, okay, using front camera or rear camera, you can observe around your face, means your face means there will be you can see a box that will means over your face, you can see a box, right? So that is actually called the bounding box. So what it will tell us is what is the top left corner of that bounding box and what is the right bottom corner. Okay, means that particular area you are interested in, because while taking photo our face should be very clear, right? So that's why you can see this YOLO actually means in your mobile also, that is but the box whatever that appeared there is called the bounding box. So the YOLO output is the object class as well as bounding box, but the mask RCN along with these two, that is, it will also give the object class as well as bounding box. Along with that, it will also provide a mask, binary mask. Okay, so this actually we are interested in vehicular accident detection. Okay, but here for this traffic pole or whatever the potholes, for all these we can use this YOLO. But the only thing why we use this mask RCN is this mask RCN will be very useful in that vehicular accident detection. Okay, but this is a complete system, right? This is a complete system for these potholes, for traffic lights. If you use YOLO and only for this for that accident detection, if you use mask, so it will be different, right? It will be means all these we must integrate as a single module, right? So at the time of integration, it will become difficult, right? So that's why for all the things, anyway, mask RCN also is giving these two along additional is giving mask. So we will not use this mask in these frameworks, but at accident detection we'll use it. Now the mask RCN, the object detection architecture, we use this mask RCN, and the mask RCN network consumes raw video frames of resolution. This is the resolution of the video frame, and it was downscaled 1920 by 1080 in 1080 pixels, but downscaled to 1024 and 1024. These video frames are sampled at 30 frames per second. The video frames are sampled at 30 frames per second. This is called refresh rate. I don't know how many of you know this, because at least in a video processing or in, I think in computer graphics, you have in I think you know this in computer graphics, we may study this. To appear as a video, there should be at least 24 frames, 24 images should be appeared over the screen per second, right? And if at least if it is less than 24 frames per second, it is less than 24 per second, 24 frames per second, so that means it will not appear to the human as a video. Simply it will appear like one picture, and then removing that picture and placing another picture, removing that picture and placing another picture. It will not appear as a video. So per second there should be at least 24 pictures should appear over the screen, then only it will appear as a continuous video. Okay, so that's why this is called that refresh rate. So it should be 24. Nowadays it is 30 frames per second, 40 frames per second also. These are producing. Anyway, whatever the videos we are taken here are 30 frames per second. Okay, and this is given as input to the mask Rcn model, and the output of the mask Rcn is the bounding boxes along with their respective masks. Okay, bounding box, respective masks, and the traffic signals, the objects. Okay, so the object class, bounding box, and mask. So the result of this phase is an output list with each element comprising the top left corner and bottom right corner spatial coordinates of the bounding box. Right? Suppose a bounding box will appear like this generally. So it will be stored like the top left corner and bottom right corner. If you have these two, you can draw a bounding box. And the detection score. What is this detection score? No, how much confidently it is saying that is a traffic light? How much confidently it is saying that is an animal, that is a dog, that is a cat? So the detection score, or we can call it as the confidence score, also it will give. Okay. So based on that, we can say that that is a traffic light, and that is the bounding box of that particular traffic light. Right. Now, anyway, this is the cropped traffic light. This is the detected object. This is the detected object. Okay. Then from this detected traffic light means this is a detected cropped traffic light. So from that, now we need to identify the color of the traffic light. You know, the color may be red, green, yellow. Okay. So to distinguish this one again from these traffic light, we need to distinguish after extracting the traffic pool, we need to identify the color of the traffic light, right? So for that, what we'll do actually we will first convert the given color image into that RGB image into HSV image, hue, saturation, and this thing. Then over that we'll perform the thresholding. What is thresholding? Thresholding is a binary. Thresholding means converting an image into binary image. Binary image means suppose generally let us assume the color range is was red color. The range is from 0 to 255 because in RGB will represent the colors from with the 8 digit, that is 8 zeros to 8 ones. 0 means complete, no red actually. The why means while increasing this color from in suppose this is 1, 2 color intensity, red intensity. So 6. So like that. Okay, while this color is the color content is increasing, this is pure red. 255 is pure red. Okay, the 0 is 0 means that just no red content is there. As the intensity is increasing, the red content that particular image will be increasing, right? So now to convert this intensities into black and white. Okay, so if a pixel is having, suppose we'll take a threshold, we'll take a threshold. We'll take a threshold. We'll take a threshold T, and if the intensity is greater than threshold, the intensity is greater than threshold, then that particular pixel will be considered as 1. 1 means white. Working properly this one. Okay. If the threshold, if the intensity is less than the threshold, the intensity is less than threshold, the intensity is less than threshold, then those pixels will be converted to 0. That is black. Okay. Now see here, this image after thresholding is converted into black and white. Means binarized image. This is called binarized image. Only two colors will be binarized image means binary means only two, right? Either 0 or 1. You can see only two colors here, right? The 44, these are in white, this is also in white, and the remaining all is converted to this, converted to 0. Now see here how it was converted. See, these color, the bright colors, the 44 and this left signal are bright compared to other background of that image. Now, if you take some threshold, okay, means less than this particular bright color. So the colors, the color intensity is less than that threshold will be 0. And as we take the threshold less than this, this bright color, they are converted into white. So this is called thresholding operation. Okay, so now we will calculate the red content, green content, yellow content, and red content in the means overall this image. Okay, using this max coverage function. So this will give us whether means this is green color is maximum or yellow color is maximum or red color is maximum. So we'll get that information in that. So based on that, whether that is a green color or yellow color or red color, will distinguish. Okay. Now, so after detection of the color, whether red or green or yellow, now we need to identify the timer value. We need to identify the timer, right? The timer and what is the value of the timer. Okay. So anyway, we have these bounding boxes, right? X1, X2, and Y1, Y2. These bounding boxes like this. Which is X1, Y1, and this is X2, Y2. This is X2, Y2 values. The output of the mask Rcn model, right? Output of the mask Rcn model is X1, X2, and Y1, Y2. So using that, now we'll find out the bounding box. From that, we'll crop that. Then see here, we need to again we need to have the colored image, right, to detect the timer. So which color and that. So the binarized image and this colored image now is performing some masking with bitwise AND operation. See here, this is the original image, this is the binarized image. This is the original image and this is the binarized image. If we multiply these two images, we'll get this thing. Why? Because multiply with 0. Suppose in the below image, the binarized image, we have only two colors, black as well as white. Black means 0, white means 1, right? So if you multiply with zeros, you'll get the complete zeros. But this bright color 44 and this what is that left arrow, they are in bright color, right? And they are in bright, and at those position in this mask will have white color. Multiply with 1, this intensity multiply with 1, you will get the same intensity. You get the same intensity, right? Now we have the complete digits only. There are we can see here. Now this will be given as input to the. This will be pre-processed actually. If there is any further pre-processed, it means enhancing the contrast. Means by using some normal histogram equation, that is called normalization method something. Right? Then we will apply this to the RetinaNet model. So this RetinaNet is again a deep learning model, like a simple convolutional neural network, right? But the main important advantage with RetinaNet model is to identify finer objects. The RetinaNet model, retina means small objects also it can identify. So mask Rcn, whatever we use it there, that is also a object detection model, but it will not function efficiently for smaller objects. So smaller objects means you can see on a traffic light, these digits will appear very small, right? Very small. These objects will appear on these digits will appear on the traffic pole very small. So to identify those digits, okay, those digits, we'll use this retina net model here. So the output of this retina net model is the digits 44, you can see. So this is the complete model. So the first we'll apply the input image to the mask RCNN. The mask RCNN output is the detected traffic pole, right? So this is the detected traffic pole, right? So that is given as input to the means retina net model. But before to that, we are generating a masked image using binarization, and the binarized image is converted into binarized image is multiplied with the original image to get this particular digits will be given to the retina net model, which will detect the digits. Okay, so this is the complete framework. Now we'll see how this mask RCN model will work. Okay, this is the output actually. The identified timer here, identified traffic pole and timer. So the wait time is, you can see here 41 because 3 minutes is over already, right? 3 seconds is over because at this moment the vehicle taken this image, but now it is, 44. So while reaching here, we can see other objects. So the wait timer is 41 now. So this is the mask RCN model. So this was developed on top on a faster RCN model. Okay, so because the faster RCNN will use two uh, will use two networks in faster RCNN. One is RPN and the other is fast RCNN. Okay, PN fast RCNN. Okay. I'm not going to that. Okay, but in mask RCNN also the mask RCNN also uses this RPN. Mask RCNN also use RPN, region proposal network. Okay, so that's why we will say this mask RCN was built on top of faster RCNN. Okay, so the mask RCN will have two stages. So you can see the complete diagram here. The complete diagram here. So the first half is this thing. The first half is this thing, stage, and the second stage is this one. Okay, so there are two stages. In stage one, again we have two networks: a backbone CNN, and a RPN. A backbone CNN and RPN. Okay, this any CNN like a ResNet model or a VGG model or a deep convolutional neural network or some other model. Okay. And we have two networks in stage one, that is a simple CNN and RPN. So the output of CNN is the feature maps, and the RPN will give us some region proposals. So what are the different objects present in there, and what about the particular region means what type of objects present in that particular image. Those region proposals will be the output of the RPN. Then in stage two, we have an ROI aligned layer, and It will also predict the object classes. See here, object classes, okay, and the object classes and the bounding box as well as the mask. Okay, the output of mask RCNN is the class, object class, right, and the bounding box and the mask. Okay, so we'll see how this will work. So image is run through the CNN to generate the feature maps. So backbone network is there, na? The backbone network. So image is run through this CNN to generate the feature maps. So RPN uses CNN to generate multiple region of interest using a lightweight binary classifier. The classifier returns object or no object scores. So what is the output of RPN? It will generate some regions, means whether that is an object of interest or no object. If that is an object, let's say that is a traffic light. So what is the score? How much confidence it is saying that is a traffic light? If it is if it is saying it as it is a human, that is a human. The object is a human. So how much confidence it is saying that is a that particular object is a human, right? So the RPN output along with the object or no object, it will also say if object what is the confidence, if no object what is the confidence. Okay, that also it will give us the output. Then the ROI aligned network outputs multiple bounding boxes rather than a single definite one and wrap them into instead of rather than a single definite one and wrap them into a fixed dimension. So the ROI aligned network, here based on the RPN will give multiple region proposals, right, depending on the objects. So for each of that object, it will the ROI aligned layer will output as different bounding boxes, and they all wrap into a fixed dimension. So the wrapped features are then fed into fully connected layers. Again, here we'll use some fully connected layers. These feature maps are given to the fully connected layers, so which will give us the bounding box dimensions as well as the classifier, the class of that object. So boundary bound prediction is further refined using the regression model. The wrapped features also fed into a mask classifier which consists of two CNNs to output a binary mask for each ROI, each region of interest, each object. It will give us a binary mask. So the mask classifier allows the network to generate masks for every class without competing among classes. So this is simple mask RCNN we used. Okay. Yeah, if you have any doubts, please ask before moving on to the next three topics. Anyway, I'll take 15 to 20 minutes. Any questions, please? Now, potential vehicle to animal accident detection. So what I said, in all the frameworks, we use mask RCNN. Okay. Here also we can use YOLO, but again we use mask RCNN to means to have a uniformity actually, right, for all the frameworks, all the support systems. So here, potential vehicle to animal accident detection. This is our vehicle, means this is the autonomous vehicle. So it has to detect the animal, whether any animal is there on the road or it is approaching the road or it is, so that is there any chance of accident or not. Okay, that we need to do it here. So here the main aim is again we need to detect the animals first. This is an object. Okay, so to detect this object again we use this mask RCNN. So same thing, right? All these animal. So the image, the frame, whatever the input frame is, this thing, it is downscaled and which is sampled at 30 frames per second. Right? This is common again. Okay. Now let us assume we detected the animal using mask RCNN. The next step, what we need to identify whether it is on the same lane. Suppose this is the lane and our vehicle is moving like this. Okay. Now, whether this animal A is on the road, on the lane, or it is somewhere here and somewhere here. Okay. If it is here, whether it is coming like this, right, or going like this, right? So this one also, if this is the object, this is the animal, whether it is coming like this or going like this. Okay, so these main whether it is on the lane or it is approaching the lane, we need to identify. Okay, so that's why first we need to identify the lane again using the previous algorithm. So the lane is used to determine if an animal is on the path of the vehicle or not, right? So countryside animals which are not on the road are not relevant to the autonomous vehicles, right? Which are not on the road are relevant. If an animal is not within the lane, we use it as the backbone for predictive feedback mechanism of approaching animals. Okay, so now we need to verify whether it is an approaching animal, whether it is approaching the lane or not. Now, animals are tracked using, so we need to verify if it is on the lane, we can easily say that. But whether it is approaching towards it or whether it is going outside of the lane. Okay. So for that, a common again simple image processing algorithm, that is centroid tracking algorithm, will use here. A simple algorithm. This one again. Okay. If an animal is outside the lane but moving towards it, we can alert the AV beforehand using the predictive feedback mechanism based on the following two regarding. The animal is outside the detected lane, animal is outside the detected lane and is moving that in the direction of towards it, or the animal is in the vicinity of the vehicle. So how we'll do that? Now I'll explain with an example. Suppose let's say some space is there, not where space is there. Okay, here I'll take this is the road. Okay, now vehicle, suppose this is our vehicle, right? Now the animal is detected somewhere here. Okay, now we'll take the centroid of this particular bounding box and we'll calculate the Euclidean distance from here to here. Okay, this is having some x distance. Now let's say if the vehicle is, sorry, if the animal is going like this in the next frame, so continuously the cam will capture the image, right? Let us assume in the next frame, in the next frame, the animal bounding boxes are here. Because it is going this side, the animal is going this side, right? Now again calculate the Euclidean distance. Again calculate the Euclidean distance. Maybe this vehicle is a little bit moved and animal also moved in that direction, right? So anyway, if we take suppose let us assume now the vehicle is somewhere here. Vehicle is somewhere here, right? Now if we calculate the Euclidean distance between that vehicle as well as the what is that bounding box of that animal. Let us assume this is y. Now tell me whether y is greater than x or not. The y will be y will be greater than x because it is going outside. So automatically the distance will increase, right? So in this situation, we can say that this is the vehicle, the object is going out of the vehicle. Okay, though, so no harm. But now say the object is, instead of going in this direction, the animal is going in this direction. Let us assume it is coming like this. closer to. It is coming like this. Now track the centroid of that vehicle. Sorry, centroid of that animal. Now tell me what is this? This is Z, the distance. You know the Z value as the vehicle is approaching the lane, the distance between this vehicle and the animal will be less. So Z is less than X. Z is less than X, correct or not? Z is less than X because the animal is approaching towards the lane, right? So the distance between those two, vehicle and animal, will be reduced. So this measure, because in the previous frame this is X, in the current frame it is Z, in the next frame it may be X, sorry, it may be some M, still it will be reduced, it will be less than, still this M will be less than Z, right? So this we can use to track the animal, this direction. Okay, so this is actually called, centroid tracking algorithm. So centroid tracking algorithm was used to track animals over successive frames using this method. Okay, anyway, you can explore this. Right. So using that information we will give as input to this predictive feedback mechanism. So based on that, it will take the decision. Okay. An animal is in the vicinity of the autonomous vehicle if its centroids lies between the horizontal midpoints of the lane. Right. So if it is in the vicinity of the lane, you can say that this animal is see, this is the lanes, right? If you draw a horizontal line, if you draw a line perpendicular to this particular object centroid and this horizontal line, if this line falls over this horizontal line, we can say that this is in the vicinity of the object is in the vicinity of the lane. Okay. So therefore, if an animal is moving towards the lane and if it is in vicinity, we can predict that animal is as a hazard for the autonomous vehicle even before it actually enters the lane. Okay. So these are some experiments actually. So you can see this animal is in front in A figure A. It is in front of that one. So here it's clearly given the instruction as stop. Right. So here also it is stop because suddenly we are able to see this, right? So here also stop signal. Right? Okay, now vehicular accident detection. Okay, I'll finish in 10 minutes. Vehicular accident detection. So here we are going to identify. So in this particular lane, while the vehicle is going on, let us assume some overlap of two objects. Okay, and their movement is zero. These we identified these two masks, means these two objects, and their movement is zero. Their speed is zero. You can say that some accident was happened, but some movement is there. They are overlapping, but some speed, some movement is there. Means with some speed they are going. Then we can say that they are moving objects. Moving objects are moving vehicles. So they are not a hazard to our vehicle, right? So that we'll see here. So procedure for vehicular accident detection. Any vehicle accident was happened in front of this vehicle, we need to identify. So first we need to identify the vehicles. So how we can identify the vehicles again using mass Rcn, same, because that is an object, mass Rcn. Right? Then in the next step, we need to track those vehicles. We need to track those vehicles. Okay. And is there any overlap? So this we will do using this. We'll use these masks, whatever the output of these masks are seen, to identify whether there is any overlap between the vehicles or not. Will by verifying their masks, you can say whether there is an overlap or not. Okay, for that actually we use this. Then if there is an overlap, in which lane they are, we need to also identify whether that overlap is within this particular lane or not. Okay, so we need to identify the lane. If they are in the same lane or like that, what is the vehicle trajectory and angle of intersection? What is the vehicle speed and change in acceleration? Okay, all these things we need to, because even though overlap is there, there is not an accident, right? If there is zero acceleration, there is zero speed, then we can say that that is an accident sometimes, right? So that is accident detection. So these are the different steps we will use. This is a flow chart. Again, for vehicle detection, we use mask Rcn, right? So this is a vehicle tracking algorithm actually. So for suppose let us assume this is the initial position of the object. This is the second position. We will find out that what is that Euclidean distance between that centroids. Okay, the distance between the centroids should be. See, this algorithm relies on taking the Euclidean distance between centroids of the detected vehicles over consecutive frames. Then vehicle overlap. If any vehicle overlap is there, the two vehicles must collide. Sorry, in any vehicular accident, the two vehicles must collide. This means that in an instant, these two vehicles must be overlapping in a frame, right? Must be overlapping in a frame. This overlapping can be easily determined if the masks are generated by the mask Rcn are overlapping by taking the intersection over union. Their mask, how much they are, what is the area underscore, area, what is the area under that intersection? Okay, intersection of IOU. Then we need to determine whether they are in the lane detection and section noise analysis actually, whether that overlapping vehicles are in the same lane or other side lanes, right? So suppose if you see our vehicle is in lane 2, right? So the left side of that lane, this particular vehicle left side lane, you can say that this is it is in section 1, right side is identified as section 3. Okay, so like this, and next we need to identify the vehicle speed and trajectories. Okay, some formulas are there anyway. Okay, yeah, this is acceleration, vehicle speed, and this absolute speed and trajectory. Some relative mechanism, relative speed of that car from previous step. Some formulas they are using. You can see, you can explore. Then using all these scores, we'll perform some weighted average over that, and if it generate a score between that will generate a score between 0 and 1. A score which is greater than 0.5 is considered as accident, else it is restarted. Simple methodology. So this is some example here. This is vehicle 1, vehicle 2, and vehicle 3, vehicle 4. Some vehicles are identified, and so okay. You can see here between vehicle 2 and vehicle 4, there is an overlap. But you can see here, vehicle 2 is having some speed and vehicle 4 is also having some speed. See here, these two vehicles, there is an overlap. Vehicle 4, this is some vehicle 4 in black color, you can observe here. There is an overlap, but some speed is there. You can say that there is no accident. Now, pothole detection, actually, we did little work over this. Still, we are doing some work here because unavailability of some data set here. See, these are the few potholes. Again, here also we'll use the mask Rcn model to detect these potholes. Okay. So here, these are the some parameters. So these are the detected potholes with confidence score. See, pothole 0.80, pothole with 1% means 100%, pothole with 0.88. This is pothole with 0.73. Right. So like that, with confidence score also it will identify these things. These are the some experiments. So this is a GPU we used for doing the experimentation, implemented in Python. These are the evaluation metrics: precision, recall, and average precision, detection ratio, false alarm rate. Means how much accurately it is detecting the accident cases. It's traffic light and counter detection. These are the intersection or union 0.5, precision, recall, success rate is also 95.65%. This traffic signal and counter was detected correctly. This precision recall curve. Uh, okay, so this is a digit recognition. So in number timer recognition, we have the values from 0 to 9. So with how much accurately the 0 was detected in the traffic pole. This is precision, the precision recall values of that one for 2, 3, 4, all these things, some experiments. Yeah. Comparative study, you can see our framework is 82%, but here it is 98%. Okay, the recall also here 88%, it is 82%, means reducing. But why I am saying our model is good, as of now, there is no paper, you can, means as per our knowledge, there is no paper, that detects these countdown timer values. Okay? So the papers, the literature is there up to the object detection. That is, they will detect only traffic lights. Traffic lights. So whatever the paper, this is a recent paper published in 2021. Okay. So here it is having 98%, but they are able to recognize only traffic lights, but not the traffic timer also. Okay. So that's why, even though it is overall less, but good. This is vehicle to animal accident detection. Again, the precision is 79%, average precision, potential accident detection ratio 84%, means accurately that accidents was detected, and false acceptance rate, falsely identified, only 0.02. Right? It was, this error should be less, so ours is good. Here it is 0.08. Okay, but ours is 0.02. Always the error should be less. Okay. So this is falsely identified these things. Vehicular accident detection and this pothole detection. Okay, this is the works. So if you have any questions, please ask. This is a simple means we last year two of my MTech students did this work, and we published in good articles. Actually, out of these work, we produced two journals and three conferences. Okay, they are published in conferences like CVIP, Control Computer Vision and Image Processing, and Indicon. Okay, so you can search in my Google Scholar for these papers related to this work. If you have any questions, please ask. No one is asking the questions. I don't know why. Any of the session.
I have a question, sir.
Sir.
Yeah. So
regarding accident detection, why are we doing accident detection?
Because see sir, if in the on that particular lane, if any accident happen, this vehicle should be slow down, right? If it detects
Okay.
any accident on that particular lane.
Hmm. No, but even without accident, if the vehicle slows down, the next vehicle will also slow down, right? Why specifically?
Right. Means based on if there is no accident, that's why we are also, that vehicle speed also we are measuring, right? Based on that vehicle speed, if they are moving very slowly, it will use some braking system. This vehicle also will slow down. But
Right.
if that is zero speed, it will assume. And sometimes there may be chance two vehicles may, because of some brake failure or something, also something will happen. The vehicle may be there on the road
Hmm.
with zero speed, means it has to
Right.
take another lane. Mean mean what happening here, so some obstacle is there on the road,
Hmm.
it may be accident. So like because in a highway, suppose in ring road, why a
Hmm.
vehicle will be means there without movement on a particular lane, if some accident
Hmm.
happen only na?
Hmm.
That's what.
Okay. No, my point is,
Sir.
why is it considered separately? So just as a part of the autonomous vehicle, what it does is it just sees if there are any obstructions. It always checks this.
Obstruction.
And then
Correct,
if
correct.
something is like, even if there was no accident and some car was just like stopped in the middle of the road,
Yeah, yeah, yeah.
some breakdown or kind of thing. So
Right, right.
that time also it will stop, right? Why
Yes,
is
yes, yes, correct, correct, sir, correct. But actually, as part of the work, we actually developed these four different frameworks. Okay, because whatever you are saying is correct. If there is an object, still
hmm.
object means no movement with zero speed, we can say there is
Hmm.
an obstacle, so you can go like this. But that will become very small project, right?
Okay. Okay.
We cannot publish because simple object detection models are there, right?
Hmm.
YOLO is there. Other
Hmm.
suppose here you can see in my screen, LK
Hmm.
song et al.
Hmm.
Used YOLO.
Okay.
But our aim is at the same time,
Hmm.
because uh, some related to autonomous vehicles, na accident means it is related to autonomous vehicles, right? So that's why, because you as a, we can club all these into a single whatever you said. That may
Hmm.
be human, that may be vehicle, that may be animal, or that may be any rock, right?
Hmm.
If any object is there on the lane, but it will become very small. That's why explore different topics actually.
Okay. Okay. Just that it's already an integral part of the autonomous vehicle operation.
Correct, correct.
Also the
Actually,
traffic.
one by one, actually we improved, sir. Actually, one by one we improved. Actually, our goal is a traffic light and signal. Later on, while working, these actually it was completed in 1 month or 1.5 month. So why to waste time? We have 1 year
Hmm.
time, right? So
Hmm.
we are means other parts of while we are why actually we don't know. This will be part of autonomous vehicle actually
Hmm.
at the time of working on this traffic light and counter detection, that one. But
Hmm.
later on, while we are means reading some literature papers, this became related to, these self-driving vehicles. Why not we cover this pothole detection, this animal detection, right? Like that, we improved actually
Okay. So why
and
was the
published one by one, sir.
why where did you consider the traffic light detection, sir, other than autonomous vehicles?
Actually, a simple while reading my research, my tech student, he
Okay.
came across some paper related to this. Okay,
Okay.
simple, anyway, it will be helpful. Means for
Hmm.
autonomous vehicles only. But
Hmm.
before doing this work, that the complete idea is not in our mind actually.
Okay. So it was just
But
image
he came with
processing.
some paper, sir. He came with some paper. He said, sir,
Okay.
only up to traffic light papers are there. So we'll do this one as well as this traffic timer detection also. right?
Okay.
When we are we finish that work and we want to publish this one while searching for the journals, actually suitable journals, they are related to transportation, they are related to these things. So why not we have 9 months or 10 months left. So like that. Anyway, same model, mask Rcn, we are using like.
Okay. Mm. Okay. Okay. So just image processing exercise.
Yeah, image processing, right?
Okay. So this image data sets, where did you get it from? Like,
Actually, this for training, we taken some that benchmark data sets for training because it has to
mm.
train properly, right? But
Mm.
for experimentation, we taken from Google only, sir. The videos, YouTube videos, all this.
Okay. So I mean, are they Indian roads or?
Not Indian roads, sir. Actually, we tried
Okay.
with Indian roads, but that not available properly because the research is also doing very less here. Okay, so
Okay.
anyway, we as of now taken the images or the videos from foreign environments only.
Okay. Probably we should build some Indian road data set also.
Yeah, yeah. Actually, we somewhere in my slide also it is there. Our aim is to develop a model for Indian roads. Actually, where it is
Okay.
there in problem.
Okay. Okay.
I
Mhm.
removed our one. For Indian road conditions only we tried first.
Mhm.
It was not there actually. In my objectives, it was there.
Okay.
Removed from this slide.
Mhm. Mhm. That may be far more difficult problem.
Yeah, yeah, yeah. Yes, sir. Yes.
It's just like now this automatic traffic lights are there, and then
Ah,
the timers, if you see, they just like jump from one number to other number.
ah, ah.
So the traffic, so
Correct, correct. Is yeah, technical issues will be there, but that is okay. That we cannot do here,
Mhm.
right? That automatic jump, there are technical problems, na, sir.
Right. Yes, sir. Thank you.
Okay, okay. Any more questions, participants? Actually, I started. It will be late because some power failure in our institute. I came home and so 20 minutes late. But okay, if you have any questions, ask quickly. Okay, if no question, then I'll leave. Actually, I have some other work. Thank you.
Okay, sir. Thank you.